The autoionization of water, or water reacting with itself. Conductivity experiments have shown that water ionizes according to the following equation. So we've got two water molecules. One of those water molecules will act like an acid and donate a proton, and one of those waters will act like a base and accept a proton in this autoionization reaction. So in this particular reaction, we've got water becoming hydronium, and we've got water becoming hydroxide. So for our, it doesn't matter which water we use, but our first water, since it's gaining a proton, by definition, we're looking at a base. And for the second water, since it's losing a proton, it's acting like an acid. Now when one of our waters gains a proton, it forms a conjugate acid. So the hydronium is the conjugate acid in this reaction. And then we're going to produce water, or hydroxide, which is our conjugate base in this reaction. Now, if we were to look at this particular reaction, we know that when we write a K expression, it's products over reactants raised to the power of the coefficient in the balanced equation. The coefficients are all ones in this particular reaction. And water is a liquid on the reactant side, and we know that we don't include those in our K expressions. So we've got a new K expression, which we refer to as Kw, or the equilibrium expression for water, equals the concentration of hydronium ions times the concentration of hydroxide ions. Conductivity experiments have determined that the concentration of hydronium ions and the concentration of hydroxide ions in pure water are both 1.00 times 10 to the minus 7. So if we plug those numbers into our Kw expression, we can calculate our value for Kw. We know that equilibrium expressions at a given temperature are constants, so Kw equals 1.00 times 10 to the minus 14. What that will allow us to do is calculate hydronium ion if we know the hydroxide ion concentration, and calculate the hydroxide ion concentration if we know the hydronium ion concentration. So let's look at a couple examples like that first. In our first example, it says, what is the hydroxide ion concentration in a water solution in which the hydronium ion concentration is 1.00 times 10 to the minus 5? So in this case, we're trying to relate hydroxide and hydronium, so we'll write our equation. Kw equals the hydronium ion concentration times the hydroxide ion concentration. Kw is a constant, 1.00 times 10 to the minus 14. We know the hydronium ion concentration, so we'll plug that in. 1.00 times 10 to the minus 5. We're trying to find the hydroxide ion concentration. So we're going to divide both sides by 1.00 times 10 to the minus 5 to solve for x, and we're going to get x equals 1.00 times 10 to the minus 9. And that's the concentration of our hydroxide ion concentration. Now, we could do this problem without using a calculator, because we know that when we divide with exponents, we're going to take those exponents and subtract them. So we've got a negative 14 subtract negative 5, and that's where that negative 9 comes from. Now, we can do a problem like this. What is the hydronium ion concentration in a solution with a hydroxide ion concentration of 6.80 times 10 to the minus 10? Again, we're comparing hydronium and hydroxide, so we'll put our equation. Kw equals our hydronium ion concentration times our hydroxide ion concentration. We'll plug in Kw, so 1.00 times 10 to the minus 14 equals, this time we're trying to find hydronium, so we'll put in our x, and for our hydroxide we'll substitute in 6.80 times 10 to the minus 10. So we're going to need to divide both sides by 6.80 times 10 to the minus 10 to solve for x. So our x will equal 1.47 times 10 to the minus 5. So we're really taking 1.00 and dividing it by 6.8. And we're taking 10 to the minus 14 and dividing it by 10 to the minus 10. Can't quite do that in our heads, but we can get a general idea. 10 to the minus 14 divided by 10 to the minus 10 is really 10 to the, or negative 14 minus negative 10, which gives us a negative 4. Since the values in front are not both 1.00, that's going to lower that number down just a little bit. Now let's look at how we're going to relate our pH to our hydronium ion concentration. We want to deal a little bit with the pH scale. pH is actually the power of the hydronium ion concentration, or pH is the negative log of our hydronium ion concentration. And when we look at our pH, we're going to be going from 0 to 14, 7 in the middle. If we have a solution that has a pH of 7, we're looking at a neutral solution. And by definition, what that means is the hydronium ion concentration is equal to the hydroxide ion concentration, which is equal to 1.00 times 10 to the minus 7. If we take the negative log of that, that's where that value of 7 comes from. Now, since it's a log function, as our pH gets less than 7, our hydronium ion concentration becomes greater than our hydroxide ion concentration, and the solution becomes acidic. The more hydronium ion we have, the lower the pH is, and the more acidic the solution becomes. If, on the other hand, our hydronium ion concentration is less than our hydroxide ion concentration, we define the solution as being a basic solution. The lower the hydronium ion becomes, the more basic the solution becomes. And the farther away from 7, the closer to 14 we get. So let's look at some examples here. Let's say we want to find the pH if we're told that the hydronium ion concentration is 1.00 times 10 to the minus 3. So pH equals the negative log of our hydronium ion concentration. So it will equal the negative log of 1.00 times 10 to the minus 3. And if we plug that in the calculator, we get our pH to equal 3.000. The number of digits in the number here tell us the number of decimal places we're going to need. So let's say that we're told our hydronium ion concentration is 6.59 times 10 to the minus 10, and we want to find the pH. So pH equals the negative log of 6.59 times 10 to the minus 10. When we plug that in the calculator, we're going to get 9.18. Okay, now let's go from pH back to hydronium ion concentration. So if we know what the pH of the solution is, we can calculate what the hydronium ion concentration is. We would take 10 to the negative pH, and that would give us our hydronium ion concentration. So let's say we want to find the hydronium ion concentration, being told that the pH is 3.0. So we would take the hydronium ion concentration equals 10 to the negative 3.0, which would give us 1.00 times 10 to the negative 3. That's pretty easy. This number here becomes our exponent. But let's say we've got 6.6 and we want to find our hydronium ion concentration. Our hydronium ion concentration would equal 10 to the negative 6.6, but we can never leave an exponent with a decimal. So we would plug into the calculator 10 to the negative 6.6, and it would give us 2.5 times 10 to the negative 7. Now this is an easy relationship. We know pH deals with the hydronium ion concentration. It's also a value called pOH, which deals with the hydroxide ion concentration. And we can calculate that by taking the negative log of the hydroxide ion concentration. And since the hydrogen ion concentration times the hydroxide ion concentration equals Kw, if we take the negative log of both of those values, we're going to get 14. So our pH plus our pOH equals 14. So pretty easy. If we're told that the hydroxide ion concentration is 2.0, and we want to find the hydrogen ion concentration, or the pH, we would take 14 minus 2. So our pH would be 12, and our solution would be basic. If we were told that the pOH is 11.2, and we wanted to find the pH of the solution, we would plug in 11.2 into our equation. 14 minus 11.2 would give us our pH, so our pH would be 2.8, and our solution would be acidic. Now, we can combine some of these steps together. Let's say we wanted to find the pH of a solution that has a hydroxide ion concentration of 1.0 times 10 to the minus 4. There's actually two ways we could do this. We could take the hydroxide ion concentration, take the negative log of that will give us the pOH, subtract it from 14, and that will give us our pH. But we also could take the hydroxide ion concentration and plug it into our Kw expression to find the hydronium ion concentration, and then take the negative log of that, and that would also give us our pH. And it doesn't matter which way you do that. So I'm going to do it the first way. I'm going to come up with the pOH of our solution. So I'm going to take the negative log of 1.0 times 10 to the minus 4. And that's going to give me a pOH of 4.00. And now I'm going to find the pH by taking 14 minus 4.00, and I'm going to get a pH of 10.00, which means that this particular solution is a basic solution. So let's say we're told that the hydroxide ion concentration is 3.45 times 10 to the minus 8, and we want to find the pH of the solution. Again, we've got two ways to do this. I'm going to calculate the pOH first and then get the pH from that value. So the negative log of 3.45 times 10 to the minus 8 is going to give me 7.462, and then my pH is going to be 14 minus 7.462, and that's going to give me 6.538. My solution is acidic. So let's just sum up our equations. We've got our hydronium times our hydroxide is going to give us our Kw. pH is the negative log of the hydronium ion. Hydronium ion is 10 to the negative pH. pOH is the negative log of hydroxide. Hydroxide is